Well, hello everybody. It's just after the top of the hour, so why don't I go ahead and get started? Looks like we have critical mass, and if people come in, they come in. So I'm Matt Larson, and I'm VP of DNS Research at VeriSign, and I got talked/asked into giving an overview here on DNSSEC. So program committee told me that there was a lot of interest in DNSSEC, and so I want to have this tutorial, and the idea is that after we're done, if you don't know what DNSSEC is, you'll come away knowing what it is, how it works at a high level, and why we need it and what it's going to do. So with that, let's begin. There should be plenty of time for questions at the end, so I'll just run through the slides, and I suppose if you have a burning question, we're a small enough group, please feel free to step to the mic and ask it, even if I'm still on the slides. So that being said, let's begin. The issue behind DNSSEC, of course, is that DNS, as it was designed originally, has no security. It just wasn't a thought put into the design of the protocol 25 plus years ago. Most DNS interactions are over UDP, so it's a single packet for a query and a single packet for a response. And because there is no security, it means that someone sending a query, which things that send queries in DNS are resolvers, it means that a resolver pretty much has to trust the source IP address of the response to match responses with queries. And this allows resolvers to be easily spoofed. Now, over the years, the state of the art of resolver implementation has gotten a lot better. And implementers have figured out how to do clever things to make resolvers paranoid and resistant to being spoofed. And that helps a lot, but that's not an ultimate solution. It doesn't completely stop things. So that has been the motivation all along for DNSSEC. And DNSSEC has an embarrassingly long timeline when you look at the implementation schedule. Well over 10 years has gone into getting DNSSEC to where it is today. As you can see, discussion started as early as 1993. There have been 3 major iterations of the DNSSEC RFCs. We sort of had Strike 1 in 1997, Strike 2 in 1999, and finally in 2005, we think we have a revised set of standards that forms the basis of the protocol as it's being implemented and deployed today. Even then, however, there were some false starts. There was something called NSEC 3 in addition to the protocol that it wasn't documented officially until 2008. So even after we had the most recent version of the base protocol specs in 05, it still took a few years before we had something that the community agreed, okay, this is something we can probably deploy. But the good news about deployment is that there have been some really significant major milestones recently. Probably the biggest of that was last year on July 15th, the DNS root zone was signed. And that's huge because, as we'll talk about, just as your browser has a list of trust anchors, of certificate authorities that it trusts, something doing DNSSEC validation needs a list of trust anchors of DNS keys that it trusts. And if you can start with just the root zone and have that as your only trust anchor and work your way from there, that's really huge from a deployment and an ease of operation standpoint. Some other milestones I've written down, mainly because I knew the exact dates because VeriSign was involved in them, that EDU was signed shortly after the root last summer. We just recently signed .NET in early December, and then the big one that a lot of people are waiting for is going to come on the last day of March this year. We're going to sign .com. So what does DNSSEC do? Well, it uses cryptography and digital signatures to provide 2 different services. The first of those is data origin authentication. So you actually know where the data came from. And in the case of DNSSEC, the thing that has a key is a DNS zone. So therefore, you can tell from a digital signature which zone a piece of DNS data came from. DNSSEC also provides data integrity. So you know that an attacker, such as a man in the middle, hasn't modified the data since it was signed. So it wasn't somehow modified in transit, or man in the middle didn't try and slip in a response a spoof response ahead of the legitimate response. That can be detected with DNSSEC. So the bottom line is that DNSSEC offers you protection against spoofing. Now, DNSSEC does not provide any confidentiality for data. There's no encryption involved here at all. The idea is that the data in DNS is public, so there's no need to keep it confidential in any way. And of course, it also doesn't address attacks against the name server itself. So things like a good old-fashioned denial of service attack or packets of death that take advantage of a buffer overrun or something like that. So, you know, it's strictly targeted at protection of spoofing. So as I mentioned just a moment ago, it's the DNS zone that has a key. And in fact, DNSSEC uses public key cryptography, so each zone in DNSSEC has a public-private key pair. Now, there are several new types of records added to DNS to handle DNSSEC. One of the analogies I like to give when talking about DNS in general is that DNS uses its own storage mechanism, if you will, to store information about DNS in DNS. And what I mean by that is that there's some kind of data in DNS that is for consumption by end users. That's the whole reason we have DNS, like, say, address records that map domain names to IP addresses. But there's other information in DNS that's just there to make DNS work, like name server records, NS records, and SOA records. So the analogy I use is like a warehouse. You know, if you have a warehouse, you can't just rent it and start throwing stuff into it. You know, the reason you rented the warehouse was to put the goods in there, but in order to be able to store anything, you have to put up shelving first. So certain pieces of DNS are like the shelving or the scaffolding, and that would be like address records and NS records. And falling into that, or excuse me, not address records, NS records and SOA records, and falling into the category of shelving, things used by DNS to make DNS itself work, would be all these various types of DNSSEC record types that I'm going to talk about. And then, of course, the things you put on the shelf would be the things that consumers care about, that end users care about, like address records and Quad A records and MX records. So anyway, the DNS key record, that's where the zone's public key is published and stored. The zone's private key has to be kept safe because this is the thing that's going to do the signing, and ideally it's stored offline. DNSSEC was specifically designed to separate signing of the data from serving of the data. So the data can be signed ahead of time. As you can see, there were some really significant design choices to make that possible. So the idea is that you can sign the data ahead of time in your locked room if you want, bring the signed data out and put it on your authoritative servers and then serve up the signed data. So this private key doesn't have to be anywhere near the internet if you don't want it to. There's no signing on the fly. All the data is signed ahead of time. So you can, if you want, keep that private key offline somewhere or you know, somewhat offline, at least not exposed right at the edge of your network where your name servers have to be. You could even store it in a hardware security module, an HSM, which are black boxes essentially that store key material securely. Unsigned data goes in, signed data comes out, and you can't get at the key material at all, or it's destroyed. So for higher profile zones like the root zone and the zones that VeriSign is signing, .com.net, that they do, you know, all that key material is kept in HSMs, and I know that other TLDs, for example, are doing likewise. So let's take a look at the DNS key record. This is what it looks like. You know, I won't go into gory details about everything up there. The main thing to take away from looking at this record is how large it is. You know, there's a lot of stuff up there. This particular key is, I believe it is, you know, it says on the bottom, it's a 1024-bit RSA public key. And so that's base 64 there. Most of what you see is the actual public key itself. So one of the biggest impacts of DNSSEC is that it makes DNS responses larger. And this is a perfect example because these DNS key records have to be handed out, and they're big. If we just look briefly at the flags, starting with the 256 or the 257, there's a 16-bit flags field that only 2 flags of which are actually defined. We have this protocol octet field that is 3, and it's always going to be number 3. Part of the consequences of having DNSSEC be this multi-year, multi-revision protocol design effort is that there's a little bit of baggage left over from earlier iterations, and this number 3 is one of them. So when we were doing the redesign in 2005, some of us, like me, argued that, hey, we essentially have a clean slate. We should just, redesign some of these records. And other people argued more loudly and persuasively that no, we don't want to do that. There's already code written. So as a result, we're going to have 3 here forever. So it's always going to be 3. Then you can use different types of public key crypto algorithms with DNSSEC. That's what you call algorithm agility. Actually, for a DNSSEC algorithm, it's a combination of 2 things, a public key crypto algorithm and a secure hash algorithm. So the data is hashed first with secure hash algorithm, and then it's signed with a public key crypto algorithm. So there's a registry, one of the many DNS registries that IANA tracks is the DNS key algorithm numbers. And number 5 happens to be the RSA public key algorithm with SHA-1 as a crypto hash. And then I already mentioned that the bulk of the record is the key itself. Now, notice we have a comment there. Anything after a semicolon is a comment in the DNS master file format. Every key has what's called a key ID. The DNS key record itself doesn't have the DNS key ID appearing in it, but it's a checksum after a fashion. It's trivially calculated and quickly calculated, and that's the idea. As we'll see, this key ID is coming up in subsequent records, and the key ID is used for somebody doing validation to very quickly find which key purports to have made a particular signature. So the idea is if a particular piece of data might have been signed by, say, 5 keys that the zone publishes, if you're doing validation, you don't want to try all 5 of those keys in an attempt to validate it. You want to try just the one that was used to make the signature, and that's what this key ID is for. All right, so speaking of digital signatures, the idea then is that the zone's private key, which we're keeping offline in a locked room with guard dogs, et cetera, that signs each what we call resource record in the zone. And a resource record, or an RR set, is the set of all records that have the same owner name, class, and type. Owner name is just the domain name. So an example here would be, let's say the domain name www.test.com in the internet class. This is yet another piece of baggage we have from the early days of DNS. The class is always going to be IN in everything you see for all intents and purposes, and then the type is A for address records. So those 3 things, that tuple defines a DNS query. It defines what records you're going to get in response, and it's that bundle of answers. So in this case, all the records, whether it be 1 or 10, that match www.test.com, class IN A, all of those records, however many, are the unit that is signed in DNSSEC and gets a signature. And that digital signature then goes in an RRSig record, short obviously for resource record signature. Now, not all information in the zone is signed. Delegation information is the most obvious exception. This would be if you think of a zone that does just or almost exclusively delegation, like .com, or some of the other TLDs, most of the other TLDs for that matter. They're mostly filled with delegation information, with NS records delegating second-level zones, and then the corresponding glue records, the address or quad A records. So that information isn't signed, the idea being that it really belongs to the child zone, the zone that's being delegated to. All right, so now let's look at the RRSig record itself. Here we have an example resource record set for www.test.com that has 2 address records. So those 2 records as a unit form an RR set, a resource record set, and it's that RR set signed. The digital signature goes in the RRSig record, and as you can see, it has several fields. Going down the list, the RRSig specifies the type of record signed. We have that digital signature algorithm again showing which combination of crypto algorithm and hash was used to generate it. You have the number of records, the number of labels in the signed name. So we have www.test.com is 3, so that 3 there after the 5 indicates that there's 3 labels in the original signed name. This has to do with how wildcards work. It's to allow DNSSEC to support wildcards. You need to know the original time to live on the cached record. so that you can substitute accordingly when you do validation. And then two really important fields, probably the most worthy of being discussed here. Signatures have what's called a validity period. They're not good forever. So in DNSSEC, a signature has a starting time and an ending time. And this is really, really significant because this is the first time in DNS that we've ever had the concept of absolute time being important. So DNS has always relied on relative time, like, a time to live has a certain value in seconds, or a refresh timer for a zone in an SOA record means that every so often the secondaries will come back and see if they should do a zone transfer. But those are all relative times. Finally, with DNSSEC, we have an absolute time. At this very moment in time, this one and only moment, the signature is good, and at this one and only moment in time, the signature is no longer good. So what this means is, once you start signing your zone, you step on a treadmill that you have to keep going on, and you can't get off of unless you decide to stop signing your zone. So it means that when you generate these records, these signatures, you can't let them expire. You need to replace them with fresh signatures with yet further out in the future validity period. And there are different strategies on how often you do that. Kind of a rule of thumb is that if your validity period is N, at probably halfway to N, at the 50% mark, you probably want to refresh the signature to have a new signature. This just always gives you plenty of buffer to never get close to the end of the signature's validity period. Because if you get to that situation and you return data and an expired signature, anybody doing validation will reject it. And that's to prevent replay attacks, where a bad guy saves a signature from the past and tries to use it in the future. In this particular example, the 41148, that's the key tag that we showed a couple of slides ago on the key itself. So this is how a validator would decide, all right, I've got a signature that was made with a particular key, and it was made with the key with key ID 41148. And if we go back a couple of slides to these sample DNS keys, here we have two of them, and you can see the first one is the one with key tag 41148. So this would allow the DNSSEC validator to quickly pick, oh yes, I know which key I should try to do the crypto validation, the relatively expensive public key operations to validate, does this signature validate, does it match the data that it purports to sign. And there's a group of a glop of base 64 that's the signature itself. Again, this is a significant size chunk of data. The recurring theme here is DNSSEC makes things larger and bigger. All right, so how do you prove something doesn't exist? We've shown how you can put signatures on data in your zone so that when you hand out a piece of data, you can say, here's the data, here's the signature over the data, so you can validate this data. But what if you give out a negative response? And there are two kinds of negative responses in DNS. There's something called a name error or an NX domain, and this is when someone asks you about a name and the name simply doesn't exist. There's no information about that name, so you hand back a response in an NX domain that says that name doesn't exist. And there's another kind of negative error, which is a no such data error, which is where they ask about a particular type of data and the name exists and has one type of data. Let's say it has an address record, but maybe somebody's asking for an MX record and it doesn't have an MX record. So that would not be an NX domain because the name actually exists. It just doesn't have the type of data that was being queried for. So both of those are negative errors, and it would be nice in DNSSEC if you could do what's called authenticated denial of existence, if you could authentically prove that something doesn't exist. Well, how do you do that? One way would be to do it on the fly, so that every time you generate one of these negative errors, you sign it. Well, that doesn't work for the reasons I described earlier. One of the fundamental design tenets is that we separate signing from serving. So this completely goes against that. You don't want to have the key material out there at the authoritative servers in order to generate these signatures on the fly. You can't really make some sort of one-size-fits-all global denial of existence for a zone saying, all right, if something doesn't exist, I'll hand back this token that says, a thing didn't exist, because you can't assert that nothing exists because that could be used by a bad guy in a replay attack. It's not specific enough. So you need something specific that says this particular thing doesn't exist. And so, indeed, DNSSEC has that, and this specific thing that gets signed ahead of time is called the NSEC record. So the NSEC record spans a gap between two domain names in a zone. So you have an NSEC record at a particular domain name in a zone, and it lists what types are at that name. And then it also lists what the next name in the zone is. And at the next name in the zone, there'll be an NSEC record that lists what types are at that name, and then lists the next name from there, and so on. And this forms a singly linked list, if you will, through the entire zone. And at the bottom, it wraps around and goes back to the top. So obviously, this notion of a next implies a canonical order for a zone, which is also something we've never had in DNS. Zones have never had an order before. They've just been data in the zone. But now there's an order, and indeed, the bottom of the slide explains what the order is. So let's take a look here. Here's a sample small zone. Nothing unusual about this. This is a very typical zone. Here's what it would look like sorted. All the names are fully qualified. Now, non-existent labels sort before existing ones, which is why test.com sorts ahead of each.test.com, and so on. So this is our canonicalized sorted version of the zone. And then here it is with the NSEC records added. The NSEC records are in bold so that they jump out at you. So again, going with our theme of DNSSEC makes things larger, you can see we've doubled the size of our zone, at least in terms of the count of resource records, because every name in the zone now gets its own NSEC record. So let's take a look at that first one for test.com. So if you just look at test.com, you can see that there's an SOA record, NS, A, MX, and NSEC. Those are the 5 types that are at the name test.com. And so then if you look on the right-hand side of that test.com NSEC record, you indeed can see 5 types there, listing the types that are present at test.com. And then before that, you see east.test.com. So this NSEC record says, all right, at test.com, we have these 5 types, and the next name in the zone is east.test.com. And then likewise, at east.test.com, we only have an NS and an NSEC there, and the next name is ns.east, and so on. This goes all the way through the zone to the bottom, which wraps around the www.nsec record, says test.com is the next name, goes back to the top. Well, what good is this? Well, for one, I should go back and point out this is an intermediate form of a zone that you'll never see in the wild. This is only for illustration purposes. This is not an unsigned zone, and it's not a valid signed zone. It's simply a zone that I've put NSEC records in to illustrate what NSEC records are. The important thing mentioned here on this slide is that every NSEC record gets a signature as well, and that's the whole point. We want something that we can sign so that we can use it to assert something. And this then is how that works. So let's say you're looking up north.test.com in the zone that I showed. Well, that name doesn't exist. There is no data at all for the name north.test.com. So this would be an NX domain response, a non-existent domain. So a name server serving a signed test.com would send out an NX domain response as usual, but it would also include this NSEC record and the corresponding signature. And what this NSEC record asserts then is, look, I have a mail.test in this zone, and the next node is named ns.test.com, and you asked for something that's between mail.test.com and ns.test.com, and I'm showing you that there is nothing between. So this NS record, backed up by its signature, asserts there is no north.test.com. It's similar for those non-existent data errors, what we call a no such data error. So let's say that you were looking up TXT records for mail.test.com. Well, if we look back in the zone, let's go ahead and do that. Mail.test.com has only an A record and an NSEC record. So you'd get back the proper DNS response that says, all right, mail.test.com, the name exists, but it doesn't have TXT records, and this same NSEC record proves that because it says, look, at mail.test.com, I have only A and NSEC types. There is no TXT type, so therefore I'm proving to you that that doesn't exist. I guess one way to think of it is if you think of the data in the zone as like bricks in a wall, the NSEC records are like the mortar that goes in between the bricks and fills in all the gaps where things don't exist. And they're a pain in the neck. They're one of the trickiest things about the whole protocol, and this is just NSEC, not NSEC 3, which I'll talk about in a moment. And there is no NSEC 1 and NSEC 2, because it would be too easy if there were. All right, so the chain of trust. There are no certificates in DNSSEC, and working for VeriSign, which until recently had a whole huge business based around issuing X509 certificates, when we would talk on the DNS side of the house to the folks on the authentication side of the house about DNSSEC, it just made their heads explode, because this is so completely different than the way things work in the X509 world. In that world you have certificate authorities, and they issue certificates, and you can go shopping around. If you have, obviously everybody knows this, if you have a website and you want an SSL cert for it, you can go pick the particular certificate authority that has, the lowest price, the best reputation, whatever your criteria are, and you know that if they're not a fly-by-night certificate authority, chances are very, very good that they are known to the various popular browsers, and so people who come access your site aren't going to be able to use it without getting some sort of pop-up error saying, hey, I have no idea who made this certificate. It doesn't work that way at all in DNSSEC. For one thing, there's not this idea of a nice wrapped-up certificate. Instead, there's just these bare keys and bare signatures, as I've described. And more importantly, the trust model is rigid. You can't go shopping around. If you're the test.com zone, you can't go to various different DNSSEC signing authorities and find somebody to sign your key. The only person who can sign your key if you're test.com is your DNS parent.com. And if you're a TLD like .com, the only entity that can sign your key is the root. So this is why it's such a big deal that the high levels of the DNS namespace are signed. That's why it's such a huge deal that the root was signed, because only the root can vouch for the TLD's keys, and that's why everyone has been clamoring for VeriSign to sign .com, because there are 90+ million .com names, and at least some of those people want to do DNSSEC, and the only way to get plugged into the DNSSEC trust hierarchy, if you will, is for .com to be signed. So the chain of trust flows from parent to child, all the way on down the namespace, just as DNS delegation does. Obviously, the root delegates to top-level domains, delegates to second-level domains, and so on. The chain of trust follows that exact same path. Now, to make things even more complicated, you don't have to do it this way, but so far, based on the deployment that we've seen, almost everyone is. There are two types of keys. What we realized, one of the things that we realized in one of the rewrites to DNSSEC is that administration is made a lot easier if you can have these two different kinds of keys. You have what's called a key signing key, or a KSK. And the KSK signs another type of key called the zone signing key, the ZSK. And then the ZSK signs all the data in the zone. And the reason that this is operationally significant is you have to tell your parent about your key. So if you have only one key, every time you change it, you have to tell your parent. So if you're test.com and you're also kind of paranoid and you think, you know what, I want to roll or change my DNSSEC key every month. Well, that would mean every time you change that key, you have to have an interaction with your parent, with .com, which means in the case of .com, you've got to talk to your registrar, you have to make the change, there are timing considerations that come into play, and that's just a pain in the neck. That means that what really could be a local operation, changing the key that signs your zone, is now hooked into this remote operation dealing with your parent. So from a DNSSEC protocol level, we decided, well, let's just decouple that. Let's have two keys. The key signing key is the one that you send up to your parent, and then it vouches for your zone signing key, and that's the one that you use to sign the zone, hence the name. So you can change the zone signing key as often as you want, and all you need to do is re-sign it with the key signing key. It's only when you change the key signing key that you need to have an interaction with your parent. So when you do have that interaction with your parent, when you tell your parent, this is my key signing key, this is what I want you to vouch for, I want you to authenticate this key to the rest of the world, the parent creates what's called a delegation signer record. I mean, this could be done by having the parent simply store the child's key in the parent zone. So for example, test.com could send its key signing key up to .com, and .com could publish test.com's full key and a signature over it and say, you know, this, you all should trust this key because I'm signing it. But remember, keys are big, so what we realized is, well, the parent doesn't have to sign the entire key. You can take a cryptographic hash of the key, and the parent can sign that instead. So that's what this DS record is. The DS record is a cryptographic hash of the child's key signing key, and then that gets a digital signature record. So here's a tiny snippet of a hypothetical.com zone. So you see the delegation information for test.com. You see its 2 hypothetical NS records, and then you see two DS records. And these DS records then contain the cryptographic hash of the key signing key from test.com. And the 2 DS records, the reason there are 2 of them is that we also have algorithm agility in the DS record. So you can, there are 2, at the moment, there are 2 different cryptographic hashes that you can use to sign, there are 2 different cryptographic hash algorithms that can be used to hash keys in a DS record. One is SHA-1, that's algorithm number 1, and as it says on the slide, the other is SHA-256, and that's algorithm number 2. So SHA-2 has a larger output size than SHA-1, which explains why that first DS record is shorter. That's a SHA-1 hash, and the second DS record is a longer SHA-256 hash. Now, you'll notice that's not base 64, that's hexadecimal. There's a reason for that, and I forget what it was, but it's yet another thing that's unfortunate and kind of confusing, in that the DNS key records and the RRSIG records store binary material in base 64, whereas the DS record stores it in plain hexadecimal. That's the most important things to say about the DS record. Note the key ID is also listed in the DS record for the same reason that it was in the RRSIG record. You want to know quickly which key to pick. All right, so let me show you how this all comes together. Here's a very small sample zone with just a few records in it, unsigned. And then when you sign it, this is what you get. As you can see, it gets bigger. I've color-coded things. We've got 2 keys there. If you look in the middle of the slide, you can see the 2 DNS key records for example.com. We have a key signing key and a zone signing key as marked on the far right of the slide. So the key signing key is in red, and you see that RRSIG in red. So the DNS keys together, all of the zone signing keys and all the key signing keys, together they form an RR set. And remember, RR sets are what gets signed. So the key signing key makes one and only one signature in your zone, and that is the signature over what we call the DNS key set. So you can see there's one RRSIG in red, and it's the signature over that entire set of DNS keys. So it's not strictly true that the key signing key signs the zone signing key. What it really does is signs all the keys, which includes the zone signing keys. Then that zone signing key is in blue, and you can see that all of the other signatures in the zone were made with that zone signing key, because they're also blue. You can see the NSEC records that were added in, they're simply in bold. So if you sort of mentally remove everything that's colored or bold, you get back to the unsigned zone. And you can see that we have significantly more signed records to support DNSSEC than we do records that would be in an unsigned zone. Once again, things get larger. Note that in this particular zone, we have a small number of names. There are only 3 different names in the zone: example.com, mail.example.com, and www.example.com. So that means only 3 NSEC records. You can count them, 1, 2, 3. But every NSEC record needs a corresponding signature. So imagine that you have a zone that has 90 million names in it. Well, that would mean 90 million NSEC records and 90 million signatures over NSEC records. Now imagine how disappointed that would make you feel to think about having to do that. So there's a way around that, fortunately. So I've already spoken about the chain of trust, the idea that parent vouches for child and so on down the DNS namespace. Well, you have to anchor that chain of trust somewhere. You have to trust somebody, and whom you trust is called a trust anchor. And DNSSEC validators, so anything that is going to validate these digital signatures, DNSSEC validators need a list of trust anchors. And these are KSKs, usually KSKs, that are implicitly trusted. The idea is that if you put a key in as a trust anchor, it means you trust it, no questions asked. This is absolutely analogous to the list of certificate authorities that is burned into your browser that I've already mentioned a couple of times. You know, your browser implicitly trusts those certificate authorities, whether they be in China or wherever. So this trust anchor store that your DNSSEC validator has, it can be updated several ways. You know, one is completely manual. It can be up to the administrator of the validator, which is usually part of what we call a recursive name server. It can be up to the administrator to maintain this file by hand, which means the administrator has to notice when the keys change for any of the trust anchors that it has. Because it's hard to notice, and one more thing you have to do, there is a protocol that everybody just refers to by its RFC number, RFC 5011. That protocol allows the DNSSEC validator to notice that a particular zone's key has gone from old key to new key, and then it can update the corresponding trust anchor in the trust anchor store. I think a lot of people are just going to get their trust anchors via some sort of trusted update mechanism, whether it be Windows Update or Yum on a Linux distribution, or you'll install a package from your vendor, even if it's source code, and it'll include sample trust anchors. So I think for a lot of people, this is going to happen behind the scenes, and they're not necessarily even going to realize it. So here's how this chain of trust works. In a perfect DNSSEC world, the root zone is signed, and finally we can say that it is. So in theory, you could get away with only trusting the root zone. You could configure the root zone's key as a trust anchor and potentially nothing else. In practice, that probably won't be the case, but in theory, that's the glorious vision that there is for DNSSEC. So you configure the root zone's KSK as a trust anchor. Your DNSSEC validator implicitly trusts the root zone key, no questions asked. So then let's say that you look up the address record for www.verisign.com. So you'll look that up, you'll get back an address record, and you'll also get back a digital signature over that address record in RRSig. And so this is how your validator forms a chain of trust. And there are different ways to write validators. You can either start this chain of trust at the top and work down, or you can start from the piece of data that you have and work your way back. But when all is said and done, you're going to have a chain of trust that looks like this. The resolver already trusts the root zone's KSK. So that means that it trusts the root zone's zone signing key, because the root zone's KSK signs all the keys in the root, including the zone signing key. In the root zone, there'll be a DS record for .com, and that DS record has the hash of .com's KSK, and that DS record is signed by the ZSK. Well, you trust the ZSK, so now you trust the authenticity of that hash of the com zone's KSK. You go query for the .com's KSK. You take its cryptographic hash, you see that it matches the hash in the DS record, and you trust the DS record, so now you trust the authenticity of the .com zone's KSK. That signs all the keys in .com, including the zone signing key, so now you trust the zone signing key. That signs the DS record for verisign.com, which is a hash of verisign.com's KSK. You trust that, therefore you trust the verisign.com's zone signing key. And finally, the verisign.com zone signing key signs the address record for www.verisign.com, and you trust that. That's how DNSSEC validation works, or in theory anyway. Now, obviously, there are optimizations here. Once you trust, just as you cache DNS information when you're looking it up, likewise you cache the results of DNSSEC validation. At least that's the way a smart validator works. Once it trusts a particular key, it'll remember that for a while, that it trusts it, so it doesn't have to form this complete chain every single time. Now, I've mentioned NSEC 3. This is an alternative to NSEC that provides two things, what we call non-enumerability and opt-out. This was a significant, I'd say bordering on heroic effort by Nominate, the .uk registry, DENIC, the .de registry, and VeriSign. We did this work leading up to the publication of the RFC in 2008. So these two things that NSEC 3 provides. The first is non-enumerability. This stops a very serious problem that, well, very serious to some people, the ability to what we call walk the zone using the NSEC records. So if you recall the way NSEC records work, they're the singly linked list through the entire zone. So all you need to do is query for something that doesn't exist in the zone, and you'll get back a negative answer that has the NSEC record and NSEC record. And so then you query the name that NSEC record points to, the next name, and you look up that name, and then you query, or excuse me, you look up that NSEC record, and then you look at the next name in that NSEC record, and you look up that name, and so on, and you can work your way all the way through the zone, and now you have a list of every name in the zone, even if the zone administrator doesn't want you to have that list. Now, this is not an issue for the generic TLDs that have agreements with ICANN, because our registry agreements require us to make those zones publicly available. It's a much different situation with some TLDs, some country code TLDs, who don't want to make their information available. And in fact, some of them said as the motivation for the work on NSEC 3 was that if you took the ability to list the contents of their zones, list all the names, combined with the information that they made available in WHOIS, that the combination of those two things together violated EU privacy laws. Now, I'm not a lawyer, but you know, that was what these certain TLDs said, and it was a big issue for .uk and .de, hence their interest in NSEC 3. And so that looked like a real showstopper for a while, because we had large European CCTLDs saying, we're just not going to deploy DNSSEC because we can't allow this zone walking. So that led to NSEC 3, and NSEC 3 works by having the chain of names not being the chain of the names themselves, but the chain of cryptographic hashes of the names. So for example, let's say you had a zone that had just 3 names in it, alpha.com, bravo.com, and charlie.com. So if it were NSEC, you'd be able to go from alpha, bravo to Charlie and back again, and around. But with NSEC 3, the chain would consist of the cryptographic hash of those 3 names. And I've just made up, for purposes of illustration, you know, 3 bogus values for what those hashes might be. But the point here is that the NSEC 3 chain is in hash order, and hash order bears no resemblance whatsoever to the actual order of the names in the zone. So yes, you can still walk the zone, you can walk the NSEC 3 chain and list all the cryptographic hashes, but that doesn't do you any good, because one of the prime characteristics of a good cryptographic hash is you can't take the hash and work backward to what the name is. So believe it or not, as complicated as this is, it can be made to work. And it's still possible to do the authenticated denial of existence that NSEC provides using NSEC 3. So this solved the problem for the European CCTLDs. It got them non-enumerability. Now, I alluded a few moments ago to one of the main heartaches that VeriSign had with DNSSEC, which is the large size of the NSEC chain. That on day one, when we would sign .com, without NSEC 3, we would have to put in 90 million NSEC records and 90 million signatures over those. It would make a huge increase in the size of the zone instantaneously, and you know that means more disk, more memory, and the biggest issue is bandwidth, and that the speed of light is only so fast. And you know, we send .com to 75 plus places all over the world, including places like Nairobi, and you know, you can only get that places so fast. So we were just very loath to have the size of the zone increase so much. And you know, that wasn't our only objection. It wasn't just because, oh, the zone's going to get bigger and we don't want to deal with a bigger zone. If you step back and think about what NSEC provides, it provides authenticated denial of existence. So what that means is you can't spoof a domain into existence. So by having every name in .com, for example, if there were an NSEC at every name, a bad guy could not spoof a non-existent name into existence with some kind of cache poisoning attack. All right. However, rather than mount such an attack, it would be much easier for the bad guy to go to GoDaddy and pay $10 and just buy the non-existent name. So what we contend is that for a zone with characteristics like .com, a very, very large zone with a policy that anybody can get any name in the zone, having the NSEC chain touch, or in this case the NSEC 3 chain touch every name just doesn't make sense. It's providing a particular kind of authenticated denial that such a zone doesn't need. So that's where this opt-out feature comes in. And this is the second feature of NSEC 3. And what opt-out does is the NSEC 3 chain only touches the secured names. So only the names that have DS records. So only the child zones who have said, all right, I'm signing my zone, here's my key material, hook me into the chain of trust. With opt-out, you can still authentically deny the existence of signed names. So signed delegations, I should say. So that means that a bad guy can't spoof signed.com into existence or change it or mess with it in any way. But it doesn't protect the unsigned names. So this has a huge impact on the size of the NSEC 3 chain because it means that there's only as many entries in the NSEC 3 chain as there are signed names in the zone. And in fact, the way things are in .NET, we actually have, I guess you'd call them bogus NSEC 3 records added because otherwise we were having issues with contention in the database because there were so few names in the zone and so few NSEC 3 records. So opt-out was another valiant effort by VeriSign, and we're very pleased that it made it into the protocol because it's huge for us. It really is the difference, we think, between being able to sign .com and really not being able to sign .com. And there are other large TLDs that are using it as well. All right, so this is my second to the last slide here. This is the what changes for DNSSEC. This is at a super high level with a sort of a bias toward the ICANN accredited registrar model. This is an illustration of the DNSSEC, the DNS landscape. We have everything in the lower left. We have a user's computer sending queries to, it should be labeled recursive name server, really not iterative resolver. An iterative resolver is merely one component of recursive name server. We have root name servers, TLD name servers. The point is, let's look at what changes if we were to deploy DNSSEC. What needs to change? Oh, well, I can see the animation building, but you can't, just barely. Well, imagine that colored boxes are slowly covering every component on the screen. No, the point is everything has to change. So let's start with the authoritative servers, the root, .com, .net, or any TLD, and then the name servers of the person who actually has the name. So all of those authoritative servers have to start serving signed data. The root, .com, let's say test.com, all of those servers have to, the zone data has to be signed, and so that means some process to sign the data, and then that means a name server that understands DNSSEC and can serve up the signed data. If we look at it specifically from the perspective of the ICANN accredited registrars and those generic TLDs, the registrars have to change their systems to accept key material from their customers, because their customers are going to say, here's my KSK, can you pass this along to the registry? The interaction that the registry has with the registrars has to change. That protocol has to be augmented to allow that key material to be passed. If we look at the left-hand side of the screen, so the right-hand side of the screen is simply publishing the signed data. And that's no good unless somebody's actually using that signed data and validating it. So that's the left-hand side, the recursive name server there that you find at ISPs and enterprises. In the early days of DNSSEC deployment, that's where we're going to see validation occur. So basically validation will occur there, and if data doesn't pass validation, it won't be sent back to the end user that requested the DNS query in the first place. But ultimately, it's reasonable to expect that the resolver portion, the DNS resolver portion of operating systems will could potentially do DNSSEC validation. The DNSSEC protocol allows for that. And even individual applications like a browser could do their own DNSSEC validation. If your level of paranoia is high and you're an operating system that doesn't want to trust your ISP's resolver because it might be lying to you, has anyone ever had their ISP's recursive name server lie to them? Send them to a... All right. So if you don't trust your ISP, you might, the OS might say, well, I want to do DNSSEC validation in a subresolver, and a sufficiently paranoid application might say, I'm not even going to trust the operating system. I'm going to do my very own DNSSEC validation. So the point is, as I look at my screen, you can't see it on yours. Everything has a shaded box covering it because DNSSEC touches everything in the DNS landscape. So my final slide then is, so what is this going to be good for? What are we actually going to use this thing for? Well, I think in the early days, DNSSEC is simply going to reduce the instances of cache poisoning because it makes it harder if data is signed, and if someone's actually doing the validation of that signed data, the bad guy can't step in the middle and spoof data and poison somebody's cache. So that I think is what we'll see in the short term. Longer term, I think when we look back on and write the history of DNSSEC, we'll see that I think this longer term benefit will be the more significant one, which is now that people can trust DNS, they'll start to use it as a secure repository where they actually put things that they care about. Because right now, if you put something in DNS, you just really can't trust the answer that comes out. Everybody uses it because we don't have any other choice. But what if it really were beefed up and fortified, and you could have an idea that, oh yeah, this piece of data that I got, it really is what the person who put it in intended it to be, and I can trust it. Well, this is just an off the top of my head, almost throwaway list of things that you could use DNS for if you could trust the responses that came out of it. One thing we're seeing right now, there's a great deal of interest on this. There's a new IETF working group called DANE, which is domain. Oh, Warren is the co-chair. It's domain authenticated. Yeah. If the co-chair doesn't even know what it stands for, that's not. Pardon? Oh yeah. All right. So, but anyway, what this working group is going to look into is the idea that what is the role of DNSSEC when it comes to X509 certificates? Would it be possible to authenticate an X509 certificate via DNSSEC rather than the traditional certificate authority model we've seen? What if www.example.com has a secure website and they generate a self-signed certificate, and we already have a cert record in DNS. You can store certificates in DNS. So what if they put a cert record at www.example.com, and this is a self-signed certificate? Actually, they could just put it in the they could configure it on the web server. Normally, this self-signed cert would cause the browser to pop up an error because the browser doesn't recognize the authority that created it. But what if there's a chain of trust that leads from the root to .com to example.com and signs that cert record, or something along those lines? The idea is DNSSEC could be used to vouch for the authenticity of the certificate. So that's something that people are very, very interested in right now. And there's various other things that you could use DNSSEC for, and many, many things that obviously are not on my list. So with that, I would be happy to take any questions you might have. Yes?
Hey, I'm Sean from Mozilla. Question about the signatures. Is there a specific reason we have an expiry time, or it's just related to the fact that it makes it, you don't sign once and forget about it?
Well, it's to prevent replay attacks, because if you didn't have a signature, if a piece of data had value A and you had a signature that lasted forever, and then you change that piece of data to have value B, and you generate another signature that lasts forever, a bad guy who had captured a signature for value A that has no expiry time could replay value A and the signature over value A forever. So that's the reason. Any other questions?
The one that's asking. Can you explain what there is a current key signing policy for root? There's a key signing party or something. you guys go about doing that?
Oh, sure. I'm trying to think of how fast I could get a slide up to describe that. I'll just describe it verbally. The route is special in that, well, many things are special about the route. Administration of the route, knowing laughs from, they're almost nervous, semi-hysterical laughs from people who know the details. Yeah. So administration of the root zone is somewhat complicated. There are three parties involved: the U.S. Department of Commerce, the IANA function at ICANN, and then VeriSign. And the design of DNSSEC for the root calls for splitting administration of the key signing key and the zone signing key. So VeriSign does the day-to-day, has historically for a long time done the day-to-day generation of the root zone and publication to the root servers. So it made sense from an administrative implementation perspective for DNSSEC to have VeriSign also sign the zone on a daily basis. So that means VeriSign creates and manages the zone signing key for the root zone. The design called for a different entity, namely the IANA function, to hold the key signing key. So ICANN has gone to a great deal of expense and effort to put a lot of policies and processes around that to make that that process of managing that key very formal and very open and transparent, so that people can look at that and go, all right, I trust what's going on here because I see they've involved the community. If you read about it, ICANN alone can't use the key signing key. It takes multiple people. This is good cryptographic hygiene to begin with. It takes multiple ICANN staff simply to get everything set up so that they could have things in place, pulled out of safes in the right room to use the key signing key in the first place. But even then, they need, what's the threshold? Does anybody remember the threshold? Is it 5 of 7? 5 of 7. Yeah. Then there are 7 crypto officers, they're called, who are trusted members of the community who applied for those positions and were selected, and 5 out of the 7 have to come together and authenticate themselves to the HSM, and only when the HSM says, okay, I see 5 out of the 7 trusted people, only now will I sign what's being asked of me. And so VeriSign and ICANN together developed a protocol where once a quarter the zone signing key changes, and the signature duration of well, we need 10 signatures a quarter, VeriSign does. So we developed an XML format where VeriSign sends this thing called a key signing request, which is similar in concept to a certificate signing request if you know the X509 world. So VeriSign sends to ICANN a KSR, a key signing request, every quarter. ICANN takes that into the secure room, one of the 2 secure rooms, has this key ceremony with 5 out of 7 people. They input the KSR into the signing equipment. When the right number of people authenticate to the HSM signs it. Out comes a document called a signed key response, which has the signatures. That gets sent back to VeriSign, and then we put it in our database, and we have the 10 signatures we need for the 9 10-day intervals for a calendar quarter. So once a quarter, there's one of these key ceremonies. The very first one, which I frankly felt privileged to be at, I was a witness to the first one when the key was actually created. Dwayne Wessels in the back of the room was at the second one at the second facility. And so far, each time there's been a VeriSign person at that ceremony to authenticate the key signing request itself. So a VeriSign person says, yeah, that thing you're about to sign, I vouch for the fact that that's the one that VeriSign produced. You're not signing bogus zone signing keys. It's the one we intended. So simply by splitting the administration of zone signing key from key signing key, there's an awful lot of policy and process that goes around that. But hopefully the idea is that the community looks at this and says, well, you guys all look like you know what you're doing, and we trust this, and it gives us confidence, and we're going to use the key. Is anyone, hopefully that didn't scare anyone from asking another question. I promise not to take 5 minutes to answer the next question, if there is one. Going once, twice? All right, well, you get 27 minutes back that you didn't think you'd have. So thanks for coming. I hope it was what you wanted.